In this lecture, we're going to look at several aspects and techniques for optimizing networks, not only in the sense of the training itself, so the optimization of the parameters that we're running to minimize the loss function, but also to improve the results of the network, for instance, selecting the right architecture or using regularization, and also speeding up the training. So we're going to see several techniques to optimize those different aspects. I'm going to start by taking a quick look at different optimization algorithms that we can use, and then how to select the best learning rate, some concerns about initializing weights. So this is a kind of thing that you already saw in practice in some exercises, but we're going to take a look in more detail at these different problems. And then we're going to look at the problem of overfitting. In supervised learning, we have a goal of making some prediction and learning to make that prediction based on some labeled data. But then we want to apply that to new data, and we need to optimize the ability of our network to make correct predictions outside the training data. So this is a problem when the predictions outside the training data are bad because the network fits too well to the training data. So we're going to review some concepts here, look at how to select models for neural networks, so how to select the architecture for our different problems, and then look at regularization methods in deep learning. So let's start with the optimizers. We are not going to look into much detail on the mathematics of function optimization, so numerical optimization, what we're doing here, but it's a good idea to understand different approaches and different optimization algorithms that you can use, especially those that you have implemented in Keras and TensorFlow. So we're going to start with the basic one, the one we saw so far, stochastic gradient descent. The very simplest version of this consists in estimating the gradient of the loss function with respect to each parameter. So remember the backpropagation algorithm that we're doing with automatic differentiation, and then multiply that gradient by a small value, the learning rate, and use that to update the corresponding parameter in our network. So we're going to do that for all the parameters in our network, and that is how the basic version of this optimizer works. A more sophisticated variant of this uses momentum. That is, it uses the gradient not to determine immediately the update to the parameter, but to determine the velocity with which the updates are made. So the magnitude of the future updates. And then we are going to use new gradient information to change that velocity. So basically, we are keeping track of how much we have changed in the past, and if this value keeps aligning, so it's always in the same direction, it starts to increase, and the parameter changes faster and faster. So this is the idea of momentum that you can include. And it's generally a good idea to include momentum because it tends to speed up learning. So we saw this with the SGD class in the optimizers on TensorFlow. Actually, this is just an alias for the class that you have in the Keras API, but we can use this one explicitly from now on because we're going to focus on this interface. Okay, but this is just one possible optimizer that you have. Another one that you have in Keras is adaptive gradient, ADAGRAD, and this one does the updates a bit differently. It keeps track of all the gradients it found for each parameter in the past. So it keeps adding all the previous gradients. More strictly speaking, it adds the square of the gradients. And then for each parameter, it will divide the learning rate by the total sum of the squared gradients so far. So this means that parameters that have small gradients will divide by a small number, and so will have a larger learning rate effectively than parameters that have large gradients. And this will tend to even out the updates on the different parameters, so that parameters for which we have less information on how they change the loss function, so the gradient is very small. Don't slow down training because they can still be updated significantly. Another property of ADAGRAD is that since it's summing all these square gradients over the training, and it's dividing the learning rate by these values for all parameters, since these values are increasing along the training, as the training proceeds, the updates will shrink. So in effect, this is like as if the learning rates are shrinking over the training. And this is a good thing for convex problems, because convex problems are those that have a minimum where we want to find for a minimum for the loss function that is inside some valley or some hole, some deep hole in the function, in the loss function. So if we are sliding down the gradients to try to find that minimum, it's a good idea to slow down as we approach the minimum to avoid overshooting and having problems with convergence. So for those kinds of problems that are convex, ADAGRAD, this trick of adding the squares of the previous gradients to slow down learning is a good one. A different approach, this RMS prop, instead of adding the square of the gradients, it keeps a moving average of the root of the squared gradients. So basically, it's averaging the last gradients it found for each parameter and keeps this mean of the squared gradients moving average. That's why it's called the RMS prop. And then it will divide effectively the learning rate or the gradient, doesn't matter. Remember that when we are doing the update, we are multiplying the learning rate by the gradient, but then RMS divides this by this moving average. So this will tend to make the update similar for all parameters, because parameters that have a small gradient at this moment will be divided by a smaller value. Parameters that have a larger gradient at this moment will be divided by a larger value, so it tends to even out. Since it's using a moving average instead of just accumulating these values like ADAGRAD does, the learning rates will not shrink. So this is good for non-convex problems where we are sliding down some loss function, but we don't have this narrow value where the minimum is. This RMS prop is often used in recurrent neural networks. You'll be seeing a bit more of those later on in the semester, but basically these are neural networks where the output is fed back in as input for another iteration, and so the same set of neurons is being reused by taking the output as input again. And this is famous for being one of the most used optimizers that was never published. It was described in a course on deep learning, and then it started to become widely used, but it was never formally published. The adaptive moment estimation, ADAM, is optimizer algorithm that brings together several of these ideas plus momentum. So it uses different learning rates for different parameters by using this exponentially decaying average of the previous gradients. So something similar to what ADAGRAD and RMS prop are doing, but using an exponentially decaying average so that it gives more weight to the most recent gradients, but also includes momentum. And so this is a very fast algorithm, and if you want, I think you could always start by trying ADAM in your problems, because it tends to learn much faster than the others, but it's a bit risky because it's a bit too greedy in this respect, trying to speed up the training, and sometimes it has convergence problems. So you notice that you get a good decrease in the loss function at the beginning, but then you start not converging and having oscillations, and things don't learn properly. So basically, the best way to choose, you can think of stochastic gradient descent, the basic one, as the safest one but slowest in general, and all the way to Adam as the one that tends to be faster when it works well, but it's a bit risky because sometimes it doesn't work very well. So what I would advise you to do is to run a few trial runs just to test, to experiment with the optimizers, and then choose the one that seems to be working best for your particular network and your problem. In some cases, for example, with recurrent networks, you could try to use RMS prop or look up the kind of algorithms that often work best with some combination of problem and architecture. But in general, you have to do some experiments to see what works best. So this brings us to how to choose these options, either the optimizer itself or adjusting the learning rate. So if you start with a very high learning rate, and I think some of you found this problem in the exercises, you can have immediately numerical overflows. So you have those not a number because you're trying to take steps that are too large and things diverge quickly. Or you can find something like this. If you see that the loss function is decreasing very fast, but then you have oscillations in the training error, this is a good indication that you are using a learning rate that is too high and you are preventing the network from converging to a good solution. Note that oscillations in the validation error are not at all uncommon because optimizing the loss function for the training set may not always improve the results on the validation set. So it may happen that you have some oscillations on the validation set. But this should not happen on the training set if everything is going well, because you should not have, after an epoch, for example, have a network that performs worse on the training set than it did on the previous epoch. This means that your network is not learning properly, and one of the reasons for this may be a learning rate that is too high. So if you see something like this, reduce your learning rate to improve convergence. Of course, if you reduce the learning rate too much, you may start to take too long to learn, so it may take a lot of epochs. And basically, you should experiment a bit. You can even do some experiments with a small subset of your training set. You will notice that there will be a lot of overfitting if you do that. But that way, by using a small subset of the data, you can see how your network is going to fit that particular set of data. And so you can check the profile for learning and see if it's converging and so on. And it's quicker to go through a number of epochs if you use a small set of data. After you do some experiments, you try to increase the learning rate, so to speed up your training, but without resulting in this kind of oscillations. This means you have a training rate that is too large. Another problem that we saw that can cause numerical problems is the initialization of the weights. Usually the bias values we set at 0, it doesn't matter, but the weights we must initialize at random to break the symmetry between the different neurons. And we saw previously in the exercise that if we use, for example, a normal distribution with a standard deviation of 1, when we add more neurons, we start getting numerical problems, especially if we use activations like rectified linear units that do not have an upper limit. The sigmoid stops at 1, but the ReLU doesn't stop at 1, and then we can have very large numbers there. So we did a quick trick, which was to divide by the number of neurons we have in the layer. There are more sophisticated methods. For example, the LeCun normal initializer uses a normal distribution with a mean of 0 and a standard deviation that is the square root of 1 over the number of connections that is coming into the neuron. So this fan in would be the number of inputs into the neuron. This is the standard, the default initialization in Keras, the Glorot uniform. It's called in Keras. This is also called normalized initialization, which uses a uniform distribution between these values, minus and plus 6 over the sum of the two fans. So fan in is the number of inputs coming into the neuron, fan out is the number of neurons which are receiving the output of the current neuron. So you add this together, 6 over this, and then the square root, and this is more or less an empirical, an heuristic for getting a good initialization, a good range of values that will not give you problems with training. But you can see more initializers in Keras documentation. In general, you will not have to worry about this, because if you don't specify anything, Keras will use this normalization here, this normalized initialization here. But you should be aware that there is this problem, and if you don't initialize the values properly, if they are too large, then you can have problems when training the network. One other thing that speeds up training of the network is standardizing the inputs. We already saw this when we work with our data. So we subtract the mean and divide by the standard deviation of all our inputs. And this helps the network because it rescales everything to the right side and centers the data. But we can also imagine a neural network, a deep neural network, as being at each layer a new network that receives as input the output of the previous layer as data. So if we were to use this standardization in all the layers or in several layers, we could improve the training of the network. And that's what batch normalization does. So this is called normalization, even though strictly speaking, normalizing is to shrink everything to a scale between 0 and 1. So actually, this is more standardizing than normalizing, but batch normalization is the name for which it's known. And the way this works is that we are computing running averages of the outputs of one layer during training. And we use those running averages to standardize the output on one layer when it becomes the input of the next layer. So before we input those values to the next layer, we standardize them by subtracting the means and dividing by the standard deviation. This is the same as we do with the data, but now we're doing that between layers along the neural network. This simplifies learning because when we are training a multi-layer neural network, each layer will have to keep relearning what it's doing as the previous layers also change the representation of the data. But this way we keep the layers from having to learn new centers and new shapes for the cloud by standardizing everything. So by standardization, we center everything at 0. The cloud of points becomes symmetrical around that center. And the only thing that changes is the actual pattern that the new layer is seeing. And there are no shifts and no variance changes. So this can speed up training a lot. And it can be done easily in Keras by adding batch normalization layers between the layers where you want to apply them. Then during training, batch normalization layers will keep this running average over all the batches. Each time we have a batch of data, it will recompute the statistics and do the standardization. And then after training, these values are frozen and we use always the same values that were left at the end of training. So these are basically issues that you have to consider for improving the training of your network, in the sense that you want it to learn as quickly as possible and with as few computations as possible. Another aspect of training is how well the network has learned. And in the case of supervised learning, this is not measured on the training data, but it must be measured outside the training data. So because we want to predict something for new data, so we need to see the performance of the network on data that was not part of the training. When we lose generalization power, when the ability to predict inside the training data is much better than outside the training data, we say that we are overfitting. The network has overfit the training data and now does not perform well outside the training data. There are two ways to solve this. We can try to adjust the architecture, so adjust the power of the model to the data that we have, or we can change the way it's trained by using regularization. So the way we want to check for this effect, for overfitting, and how we can prevent it, is to train with one set of data and use an additional set, we call it the validation set, to estimate or to choose these meta parameters in order to minimize the error outside the training data. There is also an additional set that we can use, the test set, that we can keep to the end just to get a good estimate of that error. So one way of doing these estimates that we saw last semester in machine learning is to use cross-validation. We split our training set into folds. We use all but one fold for training, and the fold that was left out we use for validation. And then we repeat, we train again with the other data points, leaving out another fold, and we do this over and over until we go through all the folds, and average these validation errors. So this is a good way of checking for overfitting, getting the cross-validation error, because it saves us data. We are using the whole training set, just using different combinations of points for training and validation. It gives us a better estimate of this error outside the training set. But in the case of deep learning, this is not a very good approach, because it requires that we train the model several times, and typically with deep neural networks this can take a long time. So cross-validation with deep learning tends to be very expensive. And also, one of the big advantages of cross-validation is that we do not need large data sets, and it helps us use our data better. But in deep learning, it's generally the case that we have large data sets, otherwise it wouldn't be worth it to use deep learning. So the best option typically for deep learning is to split our training set into training and validation, and just use one part for training and keep track of the performance of our network on validation. After we do everything, so the purpose of the validation set is to guide us when choosing how complex the network should be, which regularization methods we should use, and so on, to improve performance outside the training set. Once we have that problem solved, we may want to estimate what the true error will be after everything is done and when we use our network in real applications. So this true error would be the average error over all possible data. We cannot measure that, we don't have all possible data, but we can estimate if we use a set of examples that was never used to select anything, neither for training the network nor for selecting different models, regularization, and things like that. So everything we used for training and validation cannot be used for testing, because our decisions were guided by the error measured on those points. The solution here, like we did in machine learning, is to reserve a test set just to use for the final estimate of the true error, and don't use it to choose anything or to optimize anything. Okay, so one thing we can do to prevent overfitting is to adjust the architecture of our network the best way possible to the data that we have. For example, the exercise you did last week of the miles per gallon problem, if we solve that one, trying to predict how many miles per gallon one car will be able to run, if we use a big network like this, 100 neurons, then 50, 10, 1, you can see that there is a lot of overfitting. This is the mean quadratic, the root of the mean quadratic error in miles per gallon on the training set, so it approaches 0. It's very good at predicting on the training set, but you can see it has a significant error of about 6 miles per gallon in the validation set. So this way we can see that we have a problem of overfitting. The prediction outside the training set is significantly worse than in the training set. We can improve things a bit by simplifying the network. So this one, 30, 10, 1, gives us a slightly higher error on the training set. So you see here the blue line will jump up, but a lower error on the validation set. So it goes down here. And it is practically not overfitting. So the error is practically the same. And this would be the optimal choice possibly for this kind of problem. If we try to overdo it, then simplify too much, we start underfitting. This happens when the model cannot properly adjust to the data at all. So you can see here that the training and validation error are practically the same, but the overall error is much higher because this network only has 3 to 1 neurons, and it's too simple to try to capture the different relations between all the features. So we get a worse result. So this is one thing that you can do. You can compare training and validation error, or basically look at the validation error and select the model that minimizes the validation error, even if it happens to increase the training error a bit, because it's more important to have a low error outside the training set than inside the training set. And this brings us to a concept that we saw in the last semester between bias and variance. Basically, we can think of the error our model is committing as coming from two different sources. The bias is due to the inability of the model to adjust to the data, and it is a deviation, a bias deviation between the true values and the estimates. So we can measure that by considering the mean prediction that our model will give in different instances, so different hypotheses of the model that we get training with different data sets. In this case, the model is a curved line, a quadratic line like this. We train the model with different instances, with different subsets of this data, and we obtained different hypotheses, different specific lines. And if we measure the average prediction here and we compare it to the target value, we see that there is a distance here, and this is the bias. When we average that for all the data, this is the average bias for the model. So this bias tells us or measures the inability of the model to actually fit the data, which means that in some cases it will underestimate the value or overestimate the value, and it will tend to miss the target in a biased manner. The variance is the variance of the predictions of the model. And this is another source of error outside the training set, because if our model can adjust too much, it can overfit and start making incorrect predictions outside the training set. It loses the ability to generalize. So in this case, we simply measure the variance of the predictions, which is the difference squared between the average of the predictions and each of the predictions, and we compute the average of that value. So this is the variance for the prediction at this point, and if we average that over all the points, we get the variance for the model. Now, why this is important? Because there are different ways of trying to solve the problem of our model not performing very well, depending on whether we are underfitting, so we have high bias, or we are overfitting and we have high variance. We saw that we can adjust the power of the model by, for example, putting more neurons or something like that, but this leads to this bias variance trade-off. If the model is too simple, like we saw in the examples on the miles per gallon problem, the model cannot adjust the data, so bias is high, variance is low, but we still have a large error both on the training set and on the validation set. If we increase the power of the model, we can improve performance, but at some point the model is overfitting. So even though bias is low and training error is low, the variance can be very high, and the generalization error, the error difference between training and outside the training set, starts to increase. So by adjusting the power of the model, we can try to find the best place here. Sometimes this is not a very good place, because overfitting depends also on the size of the data set, while underfitting depends on the ability of the model to adjust to the data. So it may happen that if we have a complex problem, we need a very powerful model. Otherwise, we cannot adjust the data very well, even the training data. But a powerful model with that data set may start to overfit. So we need to try to keep this power of the model and still reduce a bit the variance that is resulting in overfitting. If we have underfitting, if the model cannot adjust the data, then we saw on the machine learning course that we have some ways of solving this, like using boosting or something like that. With deep learning, this is generally not a problem because it's easy to make the network more powerful. We add more layers, we add more neurons. Of course, this can have practical problems then when in training, but in theory, we will not be confronted with this problem of having models that are underfitting. The big problem in deep learning is often overfitting. The model has a high variance, it's too powerful, and even with a large data set, it results in overfitting. And this can be solved with regularization. So for deep learning, regularization ends up being very important because this is often the problem we need to solve. So let's see how we can do regularization in neural networks. Regularization is a change to the way the model is trained in order to reduce variance or reduce overfitting. So we are trying to restrict in some way or either overcome the problem of having few data points or restricting the freedom of the parameters so that the model cannot adjust too much to the data that we have and then start losing performance outside that training set. So one way we can do this, we already saw this kind of regularization for other models last semester, is to penalize a function of the size of the parameters. So instead of just using our standard loss function, for example, those cross-entropy functions or the mean quadratic error, something like that, we also add a regularization term that is some constant, some small value, multiplied by a function of the parameters. This function of the parameters can be, for example, the square of the magnitude of the whole vector of parameters, or the sum of the absolute values of the parameters. These are two examples of regularization. This one squared is the L2 norm regularization, and this one is the L1, the one with the absolute value. So in this case, if the parameters are too large, then the new loss function that includes that penalization increases, and so the network will try, or the optimization algorithm will try to reduce those parameters. And this works differently depending on the kind of regularization that you use. L2 regularization is also called weight decay because of the effect it has on the weights. If you consider that we have a penalization on as a function of the square of a weight, when we are computing the derivative of the loss function with respect to this particular weight w, this expression becomes 2 times the weight. So this constant alpha here remains, and basically when we want to slide down the gradient, this means that we need to subtract from the weight the learning rate, epsilon, and 2 times this alpha, the regularization parameter, multiplied by the weight itself. So you see that subtracting a fraction of the weight from the weight will make the weight shrink towards 0. Of course, in addition, we also have to use the derivative of the original loss function. So if the weight is important for minimizing the loss function or for the performance of the network, it will tend to remain at the same level. But if it's not important, if it's something that is not doing anything useful, it will start to shrink lower and lower and become smaller and smaller. So this is basically why L2 regularization is also called weight decay. We can imagine it as being an algorithm that shrinks the weights that are not very necessary. L1 regularization also shrinks the weights, but it will result in a penalty for the weight that is constant. So it's just alpha multiplied by the sign of the weight. So the big difference between the two is that whereas L2 regularization will tend to shrink all the weights and so minimize the overall magnitude of the weight vector. Some weights will be very small and so on, but the important thing here is minimizing the largest weights and shrink everything as much as possible. L1 regularization will tend to shrink some weights down to zero. So it basically makes the network sparser because some of the connections between neurons will have zero weights and will not, and those will be as if they were disconnected in those particular points. So these are two examples of regularization applying a penalty to the vector of parameters in our network, so that we restrict the way the network is being trained and we prevent overfitting. Another way of preventing overfitting is increasing the data size, the size of the data set. Of course, this is something that in general we may not be able to do because we cannot just get more data. Data is not free and freely available. But in some cases, we can create new examples from the examples that we have. For instance, consider that we have a problem of face identification. We have these images in our data set of faces, but we know that if we mirror the face, it's still a face. If we rotate it, it will still be a face. Even with some slight distortions, it must still be classified as a face. So by doing these operations, we can turn one example into several examples that are not exactly the same, and we can enrich the data that we have. So this is the idea for data augmentation. It depends a lot on what the data is that you're using. For example, if you are trying to train a neural network for character recognition, you cannot do things like this, rotations like this, because if you rotate, say, a B, it may become a P or something like that, and then you are misleading the network. But in some cases, you can do these kinds of operations and effectively increase the size of your data, and so make the network less propense to overfit the original data set. Another thing that we can do is to do data augmentation implicitly by injecting noise. This can be done in the inputs. For example, we inject random noise, uniformly distributed noise, or normally distributed noise with a small magnitude, so that we don't affect too much our inputs and don't make the inputs become mismatched with the target labels. But by adding this noise, we force our network to be more robust to slight changes in the input. And this will reduce overfitting and function as regularization. We can also do that in the output. Sometimes we have labeled data that is not 100% reliable because it was labeled by hand, by humans, and so on. So instead of using always those labels, we can put in some noise. Every once in a while, we randomly change one of the labels and give a different label to an example. This may help, in some cases, the network not overfit the training set. Or we can use label smoothing. So suppose that we are using a sigmoid activation to compute the prediction, the probability of an example being in one class or another for binary classification. Instead of using target labels of 0 and 1, we can use target labels, for example, of 0.1 and 0.9. This means that in some cases we are 90% sure it belongs to class 1. In the other cases we are 90% sure it belongs to class 0, but we never give 100% certainty to the network. So this may make the network use a shallower slope on the sigmoid function and not overfit so much. So basically, by using noise, you can reduce a bit this problem of overfitting in some cases. So this is also a form of regularization by changing the way the network is trained. A very used technique for regularization in deep learning, because it's really inexpensive, is to use early stopping. We keep track of both the training and validation error. This is a bit of a pathological example because there seems to be a lot of overfitting here. But you can see in this case that the validation error decreases, but then starts to increase again. So this happens because overfitting is becoming more and more serious as the network adjusts too much to the training set. So for this particular network, it's not a good idea to train so many epochs. It's best if we just stopped somewhere around here where the validation error was lowest. And this is the idea for early stopping. You can track the validation error of your network, and if you see that it's increasing, you move back to some checkpoint that was saved previously on the lowest point of the validation error, and that is the final network that you retain, and not the one that was trained further on, because that one has more overfitting. Another way of reducing overfitting that we saw in the last semester is bagging. Basically, we used bootstrapping to create a large number of replicas of the dataset, and then we trained our model on the large number of replicas, and when we wanted to predict new values, we averaged the predictions over all those instances, all those hypotheses. This is something that is not practical to do with deep learning, because we cannot really train 100 times our network and then retain 100 deep networks, because it's too much memory, too much time for computation and so on. But we can do this implicitly, and this is dropout in deep neural networks, especially when we are talking about fully connected layers, so the dense layers, which consists of, during training, disconnecting or turning off some of the neurons at random. So each time we present a mini batch to the network, we turn off and on neurons at random along the network. This means that each mini batch will actually be using a different network composed of different combinations of neurons in the original network. And this makes the complete network work like it was implicitly an ensemble of many different networks. And we can do bagging implicitly by training all these different networks in parallel, and then averaging the output of all these networks in the single network that we have at the end. So the way dropout works is that during training, neurons are turned off at random, and after training, the weights are all scaled by the probability of being on. So all the parameters in the network are rescaled. If this neuron was turned off half of the time, 50% of the time, then its weights will be multiplied by 2 to compensate during the prediction the times it was missing during the training. And so we this way, or we can do this, the weights are scaled dividing by 2. They are multiplied by 2 during training if we use inverted dropout. So we compensate the missing neurons by increasing the weight, or we compensate on the weights after training by adjusting them according to how often the neuron was turned on. So basically this works like bagging, because we are training many different networks, and then we are averaging them implicitly at the end once the training stops and we use the network for predictions. Another thing that we can do is to try to force our network to avoid placing the discriminants between different classes very close to examples. And this can be done with adversarial training. Consider this example. We have a network for classifying images. If we present this image, it will give us the most likely class as panda with 57% probability. If we give it this image here, it will say that it's an nematode. This is a microscopic worm, but only with a very small confidence. So basically, in this case, the network doesn't know what it is, which is reasonable because this doesn't look like anything. But if we add a very small fraction of this image to that one, and the result, when we look at the result, there seems to be no difference, because this is just 7 parts in 1,000 of this one added to that image. But the network now classifies this image as a gibbon with a 99% probability. So the reason for this is that we chose this image using the gradient of the loss function with respect to each pixel. And then we use the sign of the gradient to determine the value of the pixel. And by doing this, we are choosing an image that seems random, but it's having the highest impact on the loss function in the neural network. That is, it's being used by the neural network in the direction where it will change the classification. And so if, by adding this small fraction, we can mislead the network and lead to an incorrect result. There's lots of research in this and how to fool networks after training, but we are looking at the usefulness of this for training a more robust network, because now we can do this during training and generate images like this that will mislead the network, but then add them to the training set, so that the network now learns not to be mistaken, not to be confused by those images. And what this does, adversarial training, is it will force the network to be more constant, to have a smoother function close to the neighborhood of the training data. So it will adjust the parameters in order that it will not easily change the class just by changing very lightly the values of the input. So one problem that you probably have when considering these different options is how can you select all of these different optimizers, different methods for improving training, speeding up training, and so on. Because we don't know at the start which ones will work better. One thing you can do is simply try out a few of them manually and try to get an intuition about what works. You can try some automated search like grid search, random search, and so on, but usually the computational demands of training deep neural networks do not make it very practical to just do a kind of exhaustive search over all the different options. So my recommendation is to always do some experiments, for example, with a small subset of your data, or trying out a few different networks with a few differences in optimizers, regularization, things like that, until you get a feeling for what is working best, and then try to run the actual training for a while, so that you get a well-trained network. But there is no simple recipe for optimizing this. The idea here is just to give you the information, the knowledge about the different techniques that you can use. So to sum up this part, we saw how to optimize training, not only in the sense of choosing the optimizers that will actually reduce the loss function and fit our parameters, but also to optimize the speed of the training and optimize the quality of the result, so what the predictions are. And for this, you can consider selecting the right model, which means that you have to adjust the architecture of the network to the data and the kind of problem that you're trying to solve. And also remember that problem of bias and variance. If the network is too simple, then you'll get a large error. And too simple here means too simple for the problem that you're trying to solve, for the actual pattern that you need to find. This may happen even if you don't have a large number of examples. And then you have variance, which is the dispersion, the variance in the predictions of our model, which tends to be more serious when you have a relatively small data set. So it may happen in a deep learning problem that you need a very complex model to solve the problem, but you don't have enough data so that this complex model will not overfit. And then, so in general, you're going to need regularization to try to minimize that problem. And things that you should always use, like early stop, are easy to adapt. But then you can try other things. For example, dropout is very used also. If your data allows it, do data augmentation. That is something that if you have the right data for that, you should always use. And then there are other more sophisticated things like adversarial training, regularization, and so on, that you can experiment if it's applicable in your case. Okay, so I recommend that you read these chapters 7 and 11, and also these sections of the deep learning book. Take a look there. The book goes into more detail than what I do here on the slides, but it may help you understand this. And now we're going to take a short break, and we continue at 5 o'clock. Okay, see you soon.